This begins EE544 on Thursday, March 13th, 2014.
Thank you very much. Good afternoon, everybody. Let's continue our discussion on digital modulation techniques that we started last time. Let's review this a little bit quickly. So we do have at the transmitting side, we do have the I channel and the what? And the Q channel. And the difference between this one and the analog IQ modems is that in the analog IQ modems, the inputs are what? Are analog signals. Whereas in here, the inputs are what? Are discrete signals. In this case here, how many levels are there can be? In this case, we have what? We have 4 levels. Namely, plus or minus 1 and plus or minus what? 3. Same thing in here. Plus or minus 1 and plus or minus 3. Each of these data stream will be what? Will be modulating a carrier. The carrier is at the same frequency, but it's a different what? Different phase. One of them is a cosine, the other one is a what? Is a sine. Clear? Cosine and the sine. You can tell, by the way, that the two are what? Are orthogonal. The cosine and the sine are what? Are orthogonal. Then they get what? They get added together. So in other words, when you hear the word I channel and the Q channel, I don't want you to think in terms of what? Sending 2 different channels. It's the same channel, but it is what? Added together. Before they send it, they add it together. The I channel and the Q channel. They add it together. Now, at the receiver, they use a what? A correlator receiver or a coherent receiver to what? To separate them. Because the cosine and the sine are orthogonal to each other, this one will only give you the what? The Q channel. This one will only give you the what? The I channel. Clear? Clear? Okay, good. Now, keep in mind that when we do at the receiving side, after you multiply by the cosine, you are going to employ what? A low-pass filter to get rid of the what? To get rid of the higher frequency components. Clear? No response. Clear? Okay, good. Now, let's understand the signal constellation here. It's what we have is what? Discrete value symbols, the plus or minus 1, plus or minus 3. Every one of them will be encoded into what? Every one of these levels will be encoded into how many bits? Into 2 bits. So, for example, in here, every one of these is representing how many bits of information? 4 bits of information. 2 of them from the I channel and 2 of them are from the what? From the Q channel, creating what is known as signal constellation. Now, if you see the signal constellation here, what do you recognize? You recognize that it's a clean constellation. Why is it a clean constellation? It's a clean constellation because they are what? They are at the transmitter side. They were not involved, or they were not subjected to any interferences and so on and so forth, or noise. Clear? So at the sender side, let's see if you can help me. At the sender side, do we need boundary regions? Do we need boundary regions? What do we need the boundary regions for? We are not going to detect it at the transmitter side. It was very easy to what? To see one from the other. Clear? Because they are clean ones. The code that were used in here is what is known as what? The gray coding. In the gray coding, there will be only 1 bit that changes when you go from one symbol to an adjacent symbol. So, for example, going from here to here, there will be 1 bit changing. From here to here, 1 bit changing. From here to here, 1 bit changing. Who's the adjacent to this guy? The adjacent to this guy is this guy and this guy and this guy. Not this. Excuse me. The adjacent is the adjacent symbol to this one is this one, and this one, and this one. It's not this one. This one is not an adjacent symbol. Clear? Okay. So you use a gray coding to what? To minimize the probability of what? To minimize the probability of what? Bit error. Clear? And remember, if a symbol is in error, that does not necessarily means what? All the bits are in what? In error. A bit in here, a symbol is representing how many bits? A symbol is representing 4 bits. I remember 2 from the I channel and 2 from the what? Q channel. A symbol being in error does not necessarily means what? All the bits in the symbol are in what? In error. Clear? So in here, when you use gray coding, it means what? When you go from here to here, a symbol error has been created, but how many bits are in error? Only just 1 bit in error. Clear? Okay, good. Now, then we added to what? We added to this circuit, or we added to this system the what? The noise. That's the receiver noise. Noise is independent from what? Independent from the signal. We added the noise, and we looked at the constellation at what? We looked at the constellation at the receiving side. Clear? What do we see? We see a whole fluctuations in the what? In the signaling point. Signaling point is no longer what? Are they clean? Are they clean? They are not clean anymore. Clear? So we need to what? We need to create a boundary region to separate one from the other so that we can make a what? Excuse me. We can make what? We can make decision that minimizes the symbol error probability. Clear? Clear so far? Okay. Notice, by the way, as long as this point remains and its variation remains within the boundary region, the receiver will make the right what? Will make the right decision. It's only when the noise is what? Is bad enough to take this one to what? To here or to here or to here or anywhere else. It's where the receiver is going to make what? Errors in the decisions. Clear? Clear? Okay. Next up, what did we do? Next up, what did we do? We studied the effect of what? We studied the effect of these transitions. These are called what? Symbol transitions. Are they sharp? Are they sharp? What did we saw? We saw that their spectrum is what? It looks like this. The spectrum is looking like this. Clear? Did we do this last time or not? The spectrum is looking like this. And what can you tell me about this? This one keeps what? Keeps the side lobes keeping what? Keeping there all the time, which means what? It means that it will result in what? It will result in adjacent channel interference into channels which are operating in the nearby. Clear? Okay. So we wanted the transmitted spectrum to be what? Confined within the what? Within the band of noise. In other words, ideally we want only this. We don't want all of these things. Clear? We don't want all of these things. Remember, the channel is a what? Is a shared resource. Okay. Now, one more time. Why did we ended up with this kind of spectrum? We ended up with this kind of spectrum because the signal was changing what? The symbols were changing what? Abruptly. Abruptly. Every time you look at the signal in the time domain, if it is changing fast, that means what? In the frequency domain, you are going to get what? High frequency components. Clear? So what did we do? We shaped it. We shaped the pulses. We applied the pulses before we multiply it. Sorry, before we apply it to the IQ modulation. Before we apply it to the IQ, we shape the pulses by passing them through a what? A shaping filter. This is called a what? The shaping filter, low pass filter. What happened? All of these sharp edges got what? Got smooth. Now we have this resembling this one resembling this one. Now when you modulate, what happens? What happens is, that, by the way, what is this? This is the frequency response of the filter. The frequency response of the filter. And you can see that it's what? It's band limited. Clear? By the way, even this one here is an approximation. The actual frequency response of this one here is not what? It's not band limited. Are you following or not? Because if it is band limited, it means what? It is time unlimited. Did you get this or not? Yes or no? So this is just an approximation. But do you see how the effect of this pulse shaping filter is? It what? It reduced the amount of side lobes all the way to almost what? Zeros, and kept the what? Kept the main lobe intact. Clear? Kept the main lobe intact. So the transmit filters enable reduced bandwidth for the transmitted spectrum. In doing so, we are going to create a problem, which I will show you in just a second. The problem being what? Being intersymbol interference. every time you apply a pulse to a filter, no matter what pulse, like this or a binary pulse or something, doesn't matter. Every time you apply a pulse to a what? To a filter, which is what? Which is band limited, the output will be what? Smeared in time. Smeared in time means what? The pulses get what? Stretched in time. And if they get stretched in time, they will cause what? Interference to subsequent symbols from the same what? Source. The ISI, the way they call the ISI, they call it what? Self-interference. Self-interference means what? You are interfering with yourself. Nobody else is interfering with you. You are interfering with yourself. Clear? Okay. So it will result, as I was showing just a second, in a problem called what? Called ISI. ISI, again, as we said last time, is a form of distortion in which one symbol interfere with subsequent symbols, making the communications less reliable. Less reliable means what? The receiver is going to make what? Loss of error. Clear? Loss of errors. The reason for ISI, the major reason for ISI is through the use of, through the concept of what? Multipath communications or multipath propagation. Clear? Multipath propagation, where the signal is going to go into multiple delay paths, not the same, variable delay path, and it will be received what? At different times, hence interfering with other symbols in the future. Okay, it causes what is known as what? As blur. If you look at the image, if you are transmitting an image with multipath, the image will become what? Blurred. You will see some shadows and stuff like that in the picture. Why? Because you are interfering, it's previous symbols interfering with current symbols. The way what? The whole purpose is to design the filter, the wave shaping. The wave shaping filter, you need to design it such that it will introduce what? Minimum effect on the intersymbol interference. Clear? It try to minimize the effects of the ISI. Now, how do you judge whether there is ISI or not? You judge the ISI through the use of what? Through the use of what is known as what? I diagrams. Clear? Now, another way to see the effect is through what? Through simulating the bit error probability. Are you following me or not? Or the error vector, which I was showing just a second, the magnitude error vector, magnitude error vector, that will what? That will give you an idea about whether intersymbol interference is happening or not. Best way, of course, is the eye diagram, because you can see it very clearly whether once the eye closes, that's an indication that what? That the interference is heavy. The interference is heavy. Let's look at the diagram so that you can see what I'm talking about. What did we do here? What did we do? We applied this one to a low-pass filter, and this is before the modulation. Look at the IQ. Look at the IQ. By the way, if you look at the IQ here, you will see it wide open. Wide open means what? The eyes and the Qs are what? Are wide open. You can see them. But with the low-pass filter here, look what happened. A nice eye or not a nice eye? It's not a nice eye, all over the place. By the way, I'm hoping that you are seeing the eye. Where is the eye here? This is the eye. Do you see this eye? This eye. Normally, all of this should not be there. It should be just what? Just one open eye. Are you following me or not? Going from what? Positive to what? Negative. Did you get this or not? Yes or no? The symbols is either positive or what? Or negative. So you will get something like this. Let me show it to you. Something like this. Without these lines. Without these lines. It's what? This is what? What this corresponds to what? 1. This one corresponds to what? A 0. Are you following? Or 1 plus 1. Yes? How do we know that we are not getting what? These are symbols, adjacent symbols. I don't understand your question. These are adjacent symbols. You are looking at what? At the symbols as they what? As they are received. So wait, you mean this one is clean and this one is not clean?
No. So, like the one to your right.
This one.
Yeah. Sometimes when they do eye diagrams, there's like 2 eyes on top of each other. So like that one could look like 3 eyes.
By the way, when I say on top of each other is one for the eye and one for the what? one for the Q. All of these distortion, do you see this distortion in the middle? All of this is the result of what? ISI and what? And the noise. It's supposed to be what? Clean. So I don't understand what you mean 3 eyes. What, you mean those 3 eyes? Yeah. These, my dear, are the effect of what? The effect of noise and the intersymbol interference. The eyes is still what? Closing. This is not the real eye, is this one.
Right.
That's the real eye. I understand that, but he is talking about this one here. Just this one, a small one. This is a small one. It's not, this is for the I and the Q. This is the I. The I has how many symbols? 2 symbols. And the Q, these are separate. I'm looking at them separately. I'm not looking at them collectively. This is the I, and this is the what? The Q. And every symbol in the I represents how many bits? 2 bits. Either a what? A 1 or a what? Or a 0. The transition is either from a 1 to a 0 or a 0 to a what? A 1. Yes?
So, let's say...
Wait, hold it. The I has 2 bits and the Q has what? 2 bits. Yes. The 2 bits represent what? Every bit is representing 4. For the I, the 2 bits represent what? 4 levels, which is what? Plus 1, minus 1, plus or minus 1, plus or minus 3. On separately, on the I and the Q. Okay, continue. I understand that, but are you telling me that these eyes are clean eyes? That's what I just said. This is not a clean eye. These are not clean eyes. Once you see what all of these fluctuations, do you see these fluctuations? That results in what? That is the result of the noise and the intersymbol interference. Did you get my point or not? Yeah, what is it?
So, the top of it is, let's say -1 at the bottom of it is 1.
It depends on what. What are we using here? The levels are what? +1, -1, +3, and -3. So we have how many levels? We could have 4 levels.
2 of them are on I, 2 of them are on R.
That is correct.
Let's say we had 4 bits instead of 2 for each level. Then you would have 2 I on top of each other. Right?
Yeah, but in this case, each symbol will represent what? In other words, you will have 4 symbols, 4 bits on the I and the 4 bits on the what? On the Q. These I'm sketching it separately, sir. We are not sketching it on the same diagram. The I is one side and the Q is on the other side. So I'm not sure what you mean by 1 on top of, you mean the I on top of the Q?
Not in this case. I was referring to another hypothetical case with 4 bits instead of 2 bits.
4 bits on each, which means how many levels total? If it is 4 bits on each, it means what? It means 16 levels on each, on the I, and 16 levels on the what? On the Q. Okay, see me after the class. I cannot dwell on this one too much. We are not, either I am not understanding your question or vice versa. Okay, see me after the class. Okay, so this is the impact. One more time. Where are we? This is what the impact of the low bandwidth pulse shaping filter. Look what happens. This is not the effect of noise. Noise is not present here. In this diagram, there is no noise. As the symbols, as the signaling points get distorted, the signaling point is all over the place. Did you get this or not? Signaling point is all over the place, and you can see what you can see that you are going to create what. All of this, by the way, is the result of what? Result of all of these things here, 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 and so on, so on. Transitions. Clear? Okay. This is the effect when the bandwidth is what? Low. I want you to see the trade-off. If you make the bandwidth wide, will this one be cleaner? But on what expense? On what expense? If you make the bandwidth wide instead of low, instead of what? Narrow. If you make the bandwidth wide, will the eyes be cleaner? The eyes will be cleaner. But on what expense? On the X-axis, the noise will be higher. Why? Because the larger the bandwidth, more noise power will go into what? Into the filter. So you get what? You get those in the middle. Those things that I was just telling you about. This one. You see this? There is no crossing. Do you see there is no? Okay, 1 second. I want you to see this. Do you see those? Those are the results of what? The band limitations of the what? Of the wave shaping filter. And here, this is the effect of what? Wide. So the only thing that is ruining the eyes are what? What is the only thing that is ruining the eyes? Is the noise. Because it's this. In this case here, what is, by the way, look at the effect. Look at the effect. This is the effect of noise only. What is this? This is the effect of what? The effect of the intersymbol interference when you use what? When you use narrow filters. So the trade is what? A trade is whether you are what? Whether you are going to look at what? Increasing the noise levels by adding or by increasing the filter bandwidth, or what? Or reducing the what? Or increasing the amount of intersymbol interference if you make the filter what? Narrow. You see all of these, by the way, fluctuations in here? In here, you don't see the fluctuations, do you? You see these things. You don't see it in here. This one is what? But in here, the eyes are getting what? Are getting blurry because of all of what? Because of all of these intersymbol interference, one into the other. One symbol is interfering with the other one, and so on. So, clear? Okay. Now, now the joint. If you look at it jointly, what did you do? And you put a what? You put a low-pass filter at the transmitter, and you put a what? A low-pass filter at the receiver, and jointly, what should they be? Jointly. In other words, if you multiply the frequency response of this one with the frequency response of this one, you would like what? You would like the response to be what? Like this one. You follow me on that? Which is what? Which is close to being what? Flat in the band of what? In the band of interest. Did you get this or not? Okay. So which means what? It means that if you take a pulse in here and you what? And this is the transmit filter and this is the what? Receive filter. Which domain is this? This is in the time domain. Are you following me or not? What is ZOH stands for? ZOH, ZO. ZO means what? Zero order hold. Which means what? Once you take a sample, you hold it until what? Until the next symbol comes. Like this. I took a sample here. I hold it until what? Until the next symbol comes. I hold it until the next symbol comes. Are you following? This is called what? ZO, the zero order hold. And the P of T is what? Is the pulse shape. Clear? The pulse shape. And I'm what? Convolving, because this is in time. What is this? This is the frequency response. Sorry, this is the impulse response of the receive filter, such that the overall filter will look like what? Will look like this. It's like an ideal what? It's an ideal Nyquist type filter. Did you get this or not? Yes or no? It's Nyquist type filter. Overall, the frequency response is G of F, which is what? P of F times what? Times H of F. P of F is the pulse shaping filter, and H of F is the frequency response of the channel. Now, the top I is what? The high bandwidth. This is high bandwidth. You notice here eyes. How many eyes? 3 eyes. Yes or no? Here is what? Ooh, the eyes has what? Has all been closed because of what? Because of the lower what? Because of the low bandwidth involved. Clear? Clear? Okay, good. Now, the criteria. Can we have a criteria? Can we design a filter with that introduces zero intersymbol interference? Zero intersymbol interference. I want to show you one thing here. Listen to me. Let's assume that I'm transmitting a pulse. This is a pulse. What is the spectrum of this guy? What is the spectrum of this guy? The spectrum of this guy is this. Clear? If the next pulse is such that it is like this, will there be intersymbol interference? Let's see. During this one, if you sample the pulse exactly at the middle, What is the contribution of this guy? 0. What is the contribution of the next one? 0. But provided that you sample it exactly at what? At the middle. You lost me here. Okay, come on. I don't want to dwell on this. This is material of earlier classes. Okay, concentrate here. This is a pulse. Yes? What is the spectrum of this? The spectrum of this is like this. What is the next bit? The next symbol after this one, the next one. What is it? It will be like this. At t equal to 0. At t equal to 0. Yes? When I sample, what am I getting? Contribution from how many symbols? Only one symbol, which is which one? This one. Yes? So even though these were present, but they caused me no what? No intersymbol interference. Why? Because at this point, is I get only contribution from what? One symbol. Yes? How about this one? When I sample at this point, how many symbols? One symbol, which is what? Which is this one. The effect of this one is what? 0. The effect of, where is the next one, by the way? The next one is this. Are you following me or not? Okay, but the problem, this one here, it means what? It means at the receiver, you need to have a precise what? Timing, a precise timing. If there is a jitter, a small jitter, what will happen? Tell me what will happen. If there is a small jitter, what will you do? Let's assume that you sample it in here. Yes? Will you have intersymbol interference? You will have intersymbol interference if there is a what? If there is a jitter into timing. The effect of what? The effect of the adjacent samples will be what? Will be very heavy. Did you get my point or not? Okay, so the criteria is what? The criteria for 0 intersymbol interference, 0 intersymbol interference is the following. What is this? This is what is known as what? This is what is known as the Nyquist filtering. Nyquist filtering. You take this one in EE 567, Nyquist filtering. Okay, let's see what do we have here. What is this? What is this? That's the symbol that we are trying to transmit. Yes? And I'm representing it by a what? By a delta function. This is the filter. Did you get this or not? Yes or no? Which domain is this? Which domain is this? That's the time domain. Yes or no? Okay, in the time domain, what do you have? You have convolution of the impulse with what? With this filter, with the impulse response of the filter. What do I get? I get this. I want you to see this. Is this causing an intersymbol interference here? With who? With the next symbol. Where is the next symbol will be? Where is the next symbol will be? The next symbol will be what? Yes or no? Why? Why is the next symbol like this? Because the next symbol is coming after this one. Yes? So when you convolve it with this, it will be what? Delayed by the same what? By the same value in here, theoretically speaking. Yes or no? How many symbols do I have every second? I have what? One symbol, for example, every what? T second. Yes? In here, what am I going to have? At T, am I going to sample at what rate? 1 every what? Every T second. Every T sub S second. If the sampling is not, by the way, in here, even if it is precise, do I have intersymbol interference? Yes. Why? Because this one does not resemble what? Does not resemble what I just showed you a moment ago. I don't know where I wrote it. I thought I would not need to go. It's not like this. Do you understand that or not? This one here, if you see, there is a what? Do you see there is something here? Yes or no? You are losing me, but I cannot stay too much on this topic. I need to go on. I cannot. So if you are not following me, you need to see me in my office. The Nyquist criteria for what? Zero intersymbol interference. We need to sample the response or the output of the overall filter at the sampling period. For zero intersymbol interference, the resulting samples should have only what? One non-zero sample. All the other samples has to be what? Their contribution has to be equal to what? Zero. Clear? All of them has to be equal to zero. So the first one we are looking at is a what? A rectangular impulse response. This is a rectangular impulse response of the filter. This of G of T. Again, this is the input. What do we get? This is the output. And you can see from here, you are going to get what? You are going to get those fluctuations in here. Can we design an overall impulse response such that it spans more than one simple period and still achieve what? Zero IS. Zero ISI. It spans more than what? One simple period. What does it mean? It means the symbol is what? Is stretching, but it does not have any effect on what? On the other symbols if we sample it at what? At the right time. If we sample it at the right time. So even though the symbol is stretching, but it's not affecting what? Other symbols if we are what? If we are sampling at the right time. The answer to that is yes, through a use of a filter, which is called what? The raised cosine filter. This again, you will take it in EE 567. All of these are 567 type classes. The raised cosine filter, which looks like what? Which looks like this. This is a raised cosine filter. This is the what? This is the impulse response, and this is the what? The frequency response. You can see, by the way, when we say raised cosine filter means what? Means its characteristic resembles the what? The cosine, but it is raised. Raised means what? I don't have the what? The negative part. Did you get this or not? I don't have the negative part. Now, this is the impulse response of this filter, which is what? Sine pi t over pi t over t times this. And the impact of alpha, this alpha here, which is the roll-off factor, is clear in here. The alpha is between 0 and 1. So if you use what? The more alpha, the smaller the alpha is, the filter will become what? Narrower and narrower, resulting in what? More symbol interference. And when we get to the what? When we get to the 1 over t, which is the Nyquist, which is the smallest one, it becomes what? It becomes the ideal filter. This one here is the ideal filter here. Clear? Of a bandwidth of what? Of 1 over t, which is the symbol rate. Which is the symbol rate. Clear? Again, I want you to see this. Can you zoom in, please, a little bit? Okay. More. Hey, thank you. I want you to see this. Do you see this? This one and this one. This is for different what? For different alpha. For alpha equal to 1, for alpha equal to what? 0.5. You see this one and this one, the small one. The small one means what? Means even if there are what? Fluctuations in the time, their effect will be what? Minimal. Whereas this one, its effect will be what? Will become a little bit what? Larger. So as you vary alpha, as alpha increases, this one will become what? Will become wider a little bit. The bandwidth will become a little bit wider, but it results in what? It results in less spreading of the pulse. Clear? Less spreading of the pulse. Can you zoom back, please, a little bit? Thank you. That's the impact of the large alpha on the eye diagram. Look at the eyes here. It's pretty nice eyes. The effect of alpha, large alpha on the eye diagram, large roll-off factor leads to what? Nice open eye diagrams. Nice open eye diagrams. The key observation is what? Is that achievement of the zero ISI requires precise placement of the what? Of the sample times. We need to make sure that our sampling instants are what? Are precise. Otherwise, once we shift a little bit, we are going to get what? We are going to get errors or intersymbol interference from that missynchronization here. All of these samples, all of these are the effect of what? Of the other samples in there. Error in the placement in the sample time leads to what? Substantial ISI. Look at it. This is for alpha what? Small alpha. Look at the eye diagrams. This shrink compared with this one. Compared with this one. Better or worse? It's much worse. I reform why? Because I made alpha what? Alpha to be what? It's very small. Are you following me or not? I made alpha very small. So small roll-off factor reduces the what? The filter bandwidth. Notice, by the way, alpha is in which domain? Alpha is in which domain? When I say alpha equal to 0.5, in which domain? In the time domain. So as you make alpha what? As you, excuse me, as you make alpha what? Smaller and smaller, it reduces the what? Excuse me, reduces the filter bandwidth, which means what? It means this one will become what? Will become more sensitive to the, to the changes in the what? In the sampling instance. Clear? Clear? Okay. This is a match filter design. This one, by the way, you will take it in EE. Match filter is in EE 564. In EE 564, a match filter tells you what? It tells you that the time response or the impulse response of the filter is matched to the what? To the signal that is applied to that filter. Is applied to that filter with what? With time reversed. They call it a what? A match filter. So where you add, by the way, this one is with no noise. With no noise, just a match filter. This one is matched to this. And when you do that, you will end up with what? Each filter, again, is chosen to be the square root raised cosine. Why square root of raised cosine? Square root of raised cosine, so that when you multiply them together, you get the overall effect being what? The raised cosine. Did you get this or not? This one's called what? Square root raised cosine. SRRC. Or sometimes they just call it SRC, but if you want to be precise, it's square root raised cosine filter. Clear? Okay. Now, any question on this? Any question on this? Okay. Now, let's move on and study a little bit of what? Of different modulation techniques. This is ASK, amplitude shift king, and you can see that the amplitude is what? It's changing, whereas the frequency and the phase is what? It's not affected by. This is ASK. Rarely used, again, as I told you, a reason before, because the information is modulated onto the amplitude. Every time the information modulated in the amplitude, you are going to suffer from what? Attenuation and losses in the amplitude. This one is called what? Frequency shift king, binary frequency shift king. You need what? You need two frequencies. One of them is what? Omega C minus delta omega. The other one is omega C plus delta omega. The bandwidth occupancy of the FSK depends on what? The separation between the delta, between these two frequencies. Omega C minus delta omega and omega C plus what? Delta omega. So the separation between them is what? Is 2 delta omega. Clear? Frequency shift king can be also expanded to what? To an M array. In other words, we call it what? MFSK. MFSK. Okay, is this bandwidth efficient or bandwidth inefficient? The MFSK. Is it bandwidth efficient or bandwidth inefficient? You are guessing? Will the bandwidth increase? In MFSK, will the bandwidth increase? You are using what? You are using multiple frequencies. You are using multiple frequencies. Will the bandwidth increase? And the bandwidth will increase. Are you following or not? The bandwidth will increase. MFSK is not what? But a what? A power efficient one. It's not a bandwidth efficient. It's a power efficient. This is the other type, which is called what? Phase shift king. Again, binary phase shift king, where you are going to modulate, the information on the phase. And you can see going from 1 to 0, there is a what? There is a phase degree, a 180 degree phase shift. The constellation is like this. This is a single dimension, and this is it. This is 1, for example. This is S1, and this one is what? Is S2. The phase of this one is 0. The phase of this one is S2. Now, we already, by the way, know what is the probability of error in this case here. The probability of bit error. By the way, in this case, the probability of symbol error and the probability of bit error is the same thing. Why? Because every symbol represents what? So 1 bit. Okay, and what was it? Q square root of what? 2EB over what? NC. Close the bracket. This N0, by the way, is the what? This N0 is the noise power spectral density. The noise power spectral density. EB, of course, is what? EB is the bit energy, which is equal to what? S times what? TB, where TB is what? What is TB? Bit duration. TB is the bit duration. Clear? Okay, good. QPSK, we have a what? A quadrature phase shifting, a quadrature phase shifting. Now in here, what do we have? We have the I. By the way, in the previous one, in the PBSK, we only have what? One dimension. In other words, it's either the I or the what? Or the Q. Are you following or not? In here, we do have what? Two dimensions. So what do we have here? How many phases? Again, this one, for example, representing what? 0, 0. This one representing 0, 1. This one represent 1, 1. And this one represent what? 1, 0. Clear? Or you can shift it, by the way, by 45 degree or any other angle for that matter. Shifting, by the way, rotating the constellation does not change the what? The probability of error. The probability of error will remain the same. Okay. Are these all points on a circle? Are these points on a circle? Yes or no? Okay. However, is this a constant envelope modulation scheme or not a constant envelope modulation scheme? Not a constant. Why? Because when you go from what? When you go from one, how many transitions are allowed? How many transitions in the phase are allowed here? To go from here to here, what? Do you go around the circle or do you go straight? We go straight. So this what we have is like this. This one is what? Clear? Answer me the following question. When you go here to here, is the amplitude changing a little bit? Just a little bit. It's just changing a little bit, not much. Why? Why? Because you are almost going around the what? Around the circle. See, your amplitude does not change if you go around the what? If you go around the circle, your amplitude will not change. Is it going around the circle? It's not going around the circle. It's going to here, change here, abruptly. From zero, phase of 0 to what? Phase of 90 degree. Clear? Clear? Okay, but going from here to here, how would you go? Let's assume that the current symbols are what? 0, 0, 0 on the I, 0 on the Q, and the next symbols are what? 1, 1. 1 on the I, 1 on the Q. How would you go? How would you go from here to here? Around the circle or abruptly? Abruptly. You go this way. Did you pass through the origin? Did you pass through the origin? So what happens when you pass through the origin? What happens? What happens is that what? The amplitude becomes what? Becomes 0. The receiver might lose what? Might lose information, might lose synchronization. Are you following on now? Because during that time, he is not receiving what? He's not receiving anything. The amplitude is equal to what? Is equal to 0. Clear? Now, what does this mean? Let's see if you can tell me. It can be interpreted as two independent PBSK systems. Why? Why it can be interpreted as two independent PBSK systems? One on the what? One on the I channel, and the other one is which? This one is what? Is on the I channel. This one is on the what? On the Q channel. It's the same frequency, but it's a different what? Different phase of that frequency. We have large envelope variation occur due to the what? Abrupt phase transition, thus requiring what? Linear amplifications. When we get to the power amplifier, you will see that we require what? We require linear amplification, and if the amplifier exhibit non-linearity, we need to back off from the maximum value. This is the modulation technique again. This is the IQ, the I coming here. What does NRZ stands for? NRZ, not return to 0. Not return to 0 means what? A 1 is represented by a 1, a minus 1 represented by what? A 0 is represented by what? By a negative 1. 1, negative 1, but no transition in the middle. No transition in the middle. That's what we call the NRC. This is the odd day. In other words, this is what you have. This is the serial to what? Parallel converter. The data, the odd part will come in here. The even part will what? Will come in. Clear? Clear? Okay. Quadrature phase shifting, again, is effectively two independent PBSK systems and thereby or therefore exhibit the same performance, but at twice the bandwidth efficiency. Why? Why twice the bandwidth efficiency? How do we measure the bandwidth efficiency? Bandwidth efficiency. You are not reacting today. I'm sad to say that. You are not reacting today. I think you are looking for what? The spring break too early. RB over what? Over W. What is the units? Why is it twice? Why does it exhibit twice the bandwidth efficiency with the PBSK? Every symbol is representing how many bits? 2 bits, but the bandwidth is what? Is the same bandwidth. Why? Because you are using the same carrier, and only the phase different. One of them is a cosine, the other one is a what? Is a sine. So it's the same bandwidth occupancy, but every symbol is representing what? 2 bits. Clear? Clear? Okay, and we have large envelope variation. There's the constellation, either you have it what? The phases, zeros, 0 pi over 2, pi, 3 pi over 2, or you have what? Pi over 4, 3 pi by 4, and so on and so forth. All of these things. Clear? Clear? Okay. Now, there's the IQ channel. There's the IQ data channel. What do you notice? What do you notice? This is the what? The joint stream. What did I do? I took the what? I took the odd, yes, and I what? Stretched it. No, this is the even. I'm sorry. I said the odd. What next? D2. Next, D4. Next, D6. And similarly, what? Similarly with the Q channel. A sub what? A D sub 1. D sub 3. And so on. D sub 5. And so on. Clear? Okay, can you go from 1, 1 to 0, 0? Can you go from 1, 1, which means what? This value, from 1, 1, let's assume the code for this one, it was what? 1, 1, or 0, 0, doesn't matter. Can you go from 0, 0 to 1, 1 directly? This is it, this one. What was it? What was the value of the I? 1. What was the value of the Q? 1. Do they go to 0 at the same time? They went to 0 at the same time. That's abrupt transmission. This is how the modulated carrier look like. Modulated carrier means what? This is what is actually being what? Being transmitted. This is what is actually being transmitted. Clear? How many phases do we have? How many phases? 4 phases. And what is the relationship between the signaling rate and the bit rate? Huh? RV over 2. Where the 2 came from? Log 4. 4 is because we have 4 levels. Clear? Clear? Okay, good. Now, this is the filtered QPSK. By the way, you notice the QPSK? These are the what? These are the side lobes. Are they significant? Look at it. Are they significant? Yes, they are significant. Now, if I want to use a bandwidth filter, that's the best I could do. But the problem with the Nyquist bandwidth filter or the minimum filter is that it's not what? It's not realizable. Are you following that? It's not realizable. Why is it not realizable? Again, because it has sharp edges. And if it has the sharp edges, what does it mean? It means in the time domain, it will be what? Time unlimited. Time unlimited causes what? Causes the problems, or heavy problems on the what? On the intersymbol interference. Clear? Okay, so the Nyquist bandwidth is the minimum bandwidth that can be what? That can be used in our replay. In our replay, sorry, the maximum, what did we say? The Nyquist bandwidth is the minimum bandwidth that can be used to represent a signal. Clear? What is this, by the way? F minus FC TS. Why is this one centered at the origin? Why is this one centered at the origin? This is after modulation. Why is it centered at the origin? It is centered at the origin because I'm sketching what? F minus FC, which means what? I'm shifting it by what? By F sub C. Clear? Okay. Bit types of QPSK. Let's see if you can tell me. This is the conventional. All of these transitions are allowed. Yes? What is this? Anybody knows what this one is called? It's called what? Offset QPSK. Another name for it is what? Anybody? Huh? Anybody? Did you take 567? Anybody taking 567? No? How about 475? We did not discuss this? What is anybody? Staggered. QPSK. A better known, of course, is what? Offset QPSK. I will show you what that means in just a second. I'll get back to this in a minute. I want you to look at this and tell me what are the transitions that are allowed. Now, first of all, let me explain to you what they do. The I and the Q channel, they take one of them, usually it's the Q channel, and they delay it by 1/2 symbol duration. When I say 1/2 symbol durations, what does it mean? What does it mean? How many bit duration? So frustrating. The symbol represents how many bits? 2 bits. So when I say 1/2 the symbol duration, what does that imply? How many bit duration? 1 bit duration. So what I'm trying to tell you is the following. I want you to see this. Yes? This is the I and the Q. Can they change at the same time? Which means what? When they change at the same time means what? 1, 1 to what? 0, 0. You are going from which phase to which phase? 0 to what? 180. Delay this one by 1/2 symbol duration. Delay this one by 1/2 symbol duration. Will you be able to get a transition from 1, 1 to 0, 0? But it does not seem that you are convinced. So even though you are saying no, but it does not look like you are convinced.
Well, on the graph, they don't line up.
Forget about the graph. Forget about the graph. If you are going to delay the Q with respect to the I, by 1/2 symbol duration, 1/2 symbol duration, which is the same as what? 1 bit duration. Will you be getting 0, 0 to 1, 1 transition? You are not going to get 0, 1, 1 because they cannot change at what? At the same time. They are delayed, but they are offset by what? By 1 bit duration. Clear? So what transition do you get? What the transition do you get? Do you see the cross? No, you don't see the cross. Did you get my point or not? Yes or no? Which transition do you see? How many transitions do you see? By the way, can you go from here to here? No. Can you go from here to here? Can you stay where you are? Can you stay where you are? Yes, you can. Are you following me or not? Yes. Cannot hear you. Okay, good. Now, what did we eliminate? First of all, can you tell me the transition? The transition is what? 0 plus or minus what? 90. Do you agree? Yes or no? Transition here. Clear? Clear? What did we eliminate? We eliminated the what? The transition through what? 0, which means the amplitude, is it now closer to being constant envelope? Why? Because going from here to what? Here. By the way, is there still variation? There's still variation, because if you want to eliminate the variation, going from here to here needs to be around the what? Around the circle rather than abruptly. Clear? I delayed the what? I delayed the Q channel by what? 1/2 symbol duration, which means what? 1 bit duration. What do I need to do at the receiver? What do I need to do at the receiver? I need to delay which bit? I need to delay the I bit so that they what? So that they align one more time. Did you get my point or not? So by introducing delay, a little bit of delay, both at the transmitter and the receiver side, we eliminated what? We eliminated the transition from 0 to what? 180. The other one, let's see if you can tell me what is the purpose of this one. First of all, you need to understand it first. This is called what? Pi over 4 QPSK. This is, by the way, technology that was used in the earlier version of your digital cell phone. Digital cell phone in the US, the AT&T system, which is what? Which was based on TDMA. They use this modulation technique. Now let me explain to you first of all verbally. Is it explained here? Yes, it is. First of all, so let me show you the offset first of all. What did I do here? This is the one that you were talking about. What did I do? Tell me, what did I do? Delay this by how much? Half the symbol duration, which means what? 1 bit duration. This is what I have. So in here, for example, look at it. Is it 1-1? Here. Is it 1-1? Okay. When this one is changing, this one does not change. It changes later, which means what? What are you going from 1-1 to what? To 0-1? Yes or no? And then what? And then what? 0-0. Did you get this or not? So you will not have a what? A 1-1 1-1 transmission. Transition. By the way, do you need more bandwidth or is the same bandwidth? It's the same bandwidth. Are you following or not? It's the same power. It's just the complexity of your transmitter and receiver will increase just a little bit by introducing what? By introducing the delay in it. Clear? Okay. Let's see if you can help me. The pi over 4 QPSK. The pi over 4 QPSK. Let's understand what this is. By the way, from the title, you can tell that in pi over 4 QPSK, the transitions that are allowed is what? Plus or minus what? Pi over 4 or plus or minus what? 3 pi over 4. In other words, instead of the what? In here, what are the transitions allowed? In the offset QPSK? 0 plus or minus what? Pi over 2. Yes? This one is what? Is pi over 4 and what? 3 pi over 4. Plus or minus. You have two constellations. You have two constellations, and they are what? Offset by how much? 45 degrees. For every symbol duration, you are going to take a signal constellation, a signal point from one constellation. Clear? Clear? The other symbol, you will take a what? You will take the signal from the what? Second constellation. You alternate. One from here, one from here. One from here, one from here. Which means the transition is allowed between what and what? Could you have transition from here to here? Which is what? Which is the 90 degree. Yes? You cannot do that. Why? Because you are taking from here to here. You are not taking what? Two signal points from here. Yes? Yes or no? So it's as if you have what? How many signal points do we have? 8. But don't get fooled by 8. Each one is representing how many symbols? How many bits each symbol? Each symbol is representing how many bits in here? I have how many points? 8 points. Each symbol represents how many bits? 2 bits only. Why? Because he is going to take one from here and what? One from here. Did you get this or not? We just sketched 8 on a what? On a same circle to show that the transition is what? Is pi over 4 and what? 3 pi over 4, plus or minus. No, you didn't get it. Is this 8 PSK? It's not 8 PSK. If it was 8 PSK, every symbol represents how many bits? 3 bits. And all the constellation points are, all the signal points are from the same what? Constellation. In here we alternate between 2 constellations. Clear? Help me. Why? Let's see if you can tell me why. First of all, by the way, the transition, the previous one was what? Plus or minus what? 90. This one is what? It could be 135. Yes or no? So this one results a little bit with more what? More fluctuations in the amplitude. And instead of going what? And instead of going this way here, you are going to go what? You are going to go here this way, which means what? The amplitude resulted in what? A little bit more variation. Yes? What is the good thing about this? By the way, is it the same bandwidth? It's the same bandwidth. So you don't suffer from what? Bandwidth. But what is it easier in? Cannot hear you. No what? But you are the complexity, you are going to have two constellations. So it's the same, I mean, you know, you are going to have 2 constellations. Clear? What do you mean no delay? You shifted this by what? By pi over 4. Shifting is rotating the excuse me, rotating the constellation by 45 degrees. What, do you see something good in this? Anyway, what is the good thing? You cannot have what? 0 phase transition. Can you? Can you have 0 phase transition? Why? Why you cannot have 0 phase transition? Because you are alternating between what? 2 constellations. You are alternating between 2 constellations. And the constellations are offset from each other by how much? 45 degrees. No, you are not getting it. Say that again. You tell me. That's a good question. The question is what? Is that if you do have the same, in other words, the symbols are what? 1, 1. The next one is also what? 1, 1, 1, 1. How does it look like? How does the signal look like? No, after you detected, after you remove the demodulate, after you demodulate, what are you getting? Before sampling, you will get a straight line, which means what? It is harder on the receiver to synchronize its clock, not the carrier. I'm not talking about the carrier. I'm talking about what? The clock synchronization. It will be harder because there is no what? There is no transition. It's just a straight line. Did you get this or not? The receiver would like to see a what? Transitions in the clock so that he can what? Synchronize with those transitions. You follow me or not? Yes or no? You are losing me? Okay. If there are, listen to me. Let's assume that I have this bit pattern. Is it possible I have this bit pattern? Oh, how would this one look like? It would look like a straight line. The receiver, where should I sample here? Should I sample here? And so on and so forth. It will be confused. But if you do have a transition, if transition is required, then you are going to go from what? 1 to a what? -1, 1 minus. These transitions allow the receiver to what? Synchronize his clock. So the simplicity of what? The simplicity of the design of the clock synchronization made this technology what? Appealing for what? For TDMA base. TDMA type systems. Why? In TDMA type system, every user or every mobile will be transmitting during his what? His time slot. And if the synchronization is not proper, what will happen? What will happen? What will happen is that the information in one time slot might spill into what? Into another time slot. Did you get this or not? If the synchronization is not proper. This one, achieving synchronization is rather easy on this one. Clear? So they called it what? Pi over 4 QPSK. All of them, by the way, all of them, their power spectral density will look like what? Will look like this. That's the power spectral density. Clear? What is this, by the way? That's the main channel, and these are the what? The side lobes. What can you tell me about the side lobes? Is it taking too long to die down? It is taking too long to die down, which means what? It is not only causing interference to the adjacent channel, but it will also cause interference to what? To some channels which are what? Not to the adjacent what, but the adjacent to the adjacent. Did you get this or not? I want to show you a diagram. Let me, before I get to this, let me show you, jump a little bit. The minimum shift keying. This one, by the way, is called the Gaussian minimum shift keying. We'll talk about this in a minute, but I just want to show you something here. This is, by the way, this is the technology modulation used in GSM. GSM stands for the Global System for Mobile Communications. Again, it's a what? TDMA-based, time division multiple access. But this one is the European standard, the one that is used in Europe, and also the one that is used in the US, but not in the cellular band, in the PCS band, in the personal communication services band. I want you to tell me, look at their spectrum, the solid one. Can you zoom in, please, a little bit? More. Hey, thank you very much. Do you see the solid? The solid is QPSK. The dotted is what? Is the GMSK. Yes? Tell me, what do you see? Tell me, what do you notice? First of all, the male lobe. Look at the male lobe. Which one is a bit wider? The GMSK is a little bit wider. The male lobe. Yes or no? Okay, but I want you to see the side lobes. Which one are dying faster? The GMSK is dying faster. The reason, in the GMSK, when you go from one symbol to another symbol, you are going around the what? Around the circle rather than what? Abruptly. And when you go around the circle, the amplitude is not going to what? Is not going to change. And the phase is changing continuously rather than what? Abruptly. Abruptly means what? Going from 0 to 90 right away. This one you are going to what? By the way, I will show you in the diagram. You see the phase? The phase is changing what? The phase is changing what? It's continuously. Are you following me or not? Yes or no? I will show you this in just a second. Now, this is the distortion. This is a perfect channel. Perfect channel means what? No noise. No noise. No what? Jitter, no nothing. What is this? This white noise. Tell me, why is it in circles? In the white noise. Why is it in circles? The white noise means what? White noise means what? Means the fluctuations, the values can take from where to where? Minus infinity to infinity, and the phases are all over the place. Uniformly distributed between 0 and 2 pi. Tell me the phase jitter. Can you show me the phase jitter? The phase jitter. Phase jitter means what? There is a fluctuations in the what? In the phase. Yes? You see, it's going this way here. The magnitude did not change. It's only the what? Only the what? Only the phase. Because it's going around what? Around the circle. We call it a what? A phase jitter. And the white noise, it's in all directions. This one is in all directions. This is in what? Just around the circle. Clear? Okay. Now, this is the amplitude distortion. Let's see if you can tell me about the amplitude distortion. Where did the amplitude distortion came from? The amplitude distortion came from the fact that the devices are what? Are nonlinear. Are you following? The devices are nonlinear. That was the linear device. That would have been the linear device. Clear? No response. Clear? Okay. Now this is what we have. AM distortion. What does AM distortion means? We have AM, and then in a minute I will show you the what? The AM what? PM distortion. Clear? The AM PM distortion. And this AM, what is it? Is that any fluctuations in the what? In the AM results in what? In AM distortion at the output. Did you get this or not? They call it AMA. Tell me what happened here. Did the phase change, theoretically speaking? Did the phase change or only the amplitude? Only the amplitude, which means what? The points are going what? In a radial fashion. Did you understand that or not? Yes or no? Okay. In RF, the amplitude variation in the environment, say from multiple reflections and so on and so forth, is larger than the what? The phase variation. In a what? In a multiple reflections environment. Use PSK in a mobile environment. Mobile environment results in a bigger amplitude variation than what? Phase variations. Clear? Clear? Okay. Now, let's see if you can help me with the next one. No, this one we already did. By the way, there's a typo in here. Figure it out. There's a typo. We did this one in class. I just copied it from Steer, but he has a typo. You remember we got it? How much we got it? The par. The par for this. 6 dB. Yes? The mistake that he made is what? Is the power of the peak RF is proportional to what? 1/2. Why 1/2? Do you understand that or not? This 1/2 is a typo. The power is what? Is A plus B, the whole thing what? Square. Which means what? 2x squared. You put 1/2. The 1/2 is only for the average. This is for the average, not for the peak. Okay, so correct this mistake here. What is this? Tell me what is happening here. Phase distortion. Why? The amplitude distortion is what? Is because of the nonlinearity. Yes? Okay, what is the phase distortion from? Where is it coming from? If the system does not introduce any phase distortion, what should the phase characteristic be? If the system does not, I tell you, I have a system that does not include or introduce any phase distortion. When I say phase distortion means what? No pulse what? Smearing. Delay is okay, but no pulse what? Smearing. What should the phase characteristic be? What should the phase characteristic be? Okay, you are struggling with this. Okay, let's look at it very carefully here. I have a system. Let's assume I apply what? X of t. And I get what? Y of t equal to what? A x of t minus t0. Answer me the following question. Was the pulse smeared or just delayed? What is the frequency response of this filter? This filter is said to be a what? A distortionless filter. A distortion filter. By the way, did the amplitude change? It just got what? Scaled. Did you understand that? Or I just get scaled. What is this? So this is what? X of what? X of f. What is this? Y of f equal to what? A e to the what? A. X of f times what? 2 pi f. So 2 pi f times t0. Why? Delay in the time domain corresponds to multiplication of the frequency response by this. Yes? So what is h of f? What is it? What is it? How do I sketch this? The magnitude? Yes or no? Is it for all frequencies? For all frequencies, what is the phase? So this is the absolute value of h of f. What is the phase? This f. This is f. Still waiting. Where is the phase? Can you give me where is the phase first of all? This is the phase. Yes? And because we have a minus sign, so what do I have? Yes or no? Okay, what is the slope of this guy? Minus d phi differentiate with respect to what? With respect to omega or 2 pi f? Yes or no? Which means what? What do you get? With a minus. So it's what? D by df? 1 over 2 pi? Yes or no? Help me. Constant delay? That's constant delay. So if you see a phase which is what? Linear, passing through who? Passing through the origin, that system does not introduce what? Phase distortion. Is it? Is this one linear or not linear? Notice, by the way, from this portion, it is what? Linear. Did you get this or not? But once you get this portion here, what will happen? The linearity is what? Is gone, which means it will introduce phase distortion. Show it to me. Where is the phase distortion? Is the amplitude changing? No, the amplitude changing is just what? The phase is changing. Did you get this or not? Yes or no? Oh, now.
5-minute warning, Professor.
What happened?
5-minute warning. Yep.
Okay, you scared me. Okay, now, what is this? This distortion due to the what? Noise, not to the what? The nonlinearities. Distortion due to the noise. What do you see? This, by the way, do you see this circle? The wide one? This, the without distortion. What is it? Noise affects it in what? In all directions equally. You follow me or not? In all directions equally. Now, one more parameter to introduce you to the following, which is extremely important. I need you to understand this very carefully. Very carefully. You will not study this in other classes. So you need to understand this is crucial in RF, which is called what? EVM. EVM stands for what? The error vector magnitude. The error vector magnitude. This is a measure of what? Of the distortion. A measure of the distortion. Similar to what? Signal to noise ratio. Are you following me or not? This is another measure which is more widely used in RF. Are you following me or not? The EVM. Let's understand so that you understand what I'm talking about before we get into the equation. Let's get to the equation first. EVM is the absolute value of what? Where is the ideal here? This is the ideal. Clear? This is the amplitude distortion. This is the what? The phase distortion. This is what? With the noise. All of them resulted in what? All of them resulted in what? In the moving of this point to where? This point. Yes? You measure this one, which is what? The ideal case. Yes? And then you measure what? You measure this one. And EVM is the ratio of the absolute value of X error divided by what? Absolute value of the reference. Did you get my point or not? Voltage. Everything here is what? Is voltages. Notice, by the way, this is the reference. This is from the measurement. I am measuring the what? The received voltage. Yes or no? I'm right. Is it the same or they are not the same? So I sketch a vector here, the reference. I have another one here. The difference between them is called what? X error. Are you following or not? Yes or no? Okay. Why am I taking the absolute value? Could it be on the other side? In other words, could it be lower than this one? It could be lower than this one. So, but it doesn't matter whether it's what? Above or below. It's still an error. Did you get this or not? So I take the absolute value. Now, explain this one to me. Where this equation came from? Where does this equation come from? What? This is the X man, and what? This is the error. You see this error? I break it into what? Into the Q and the what? I. And what am I doing here? Question. Do all of them have to be distorted the same way? All of the symbols, all of these signal constellations, do they have to be distorted the same way? So what am I doing here? Can you explain to me what am I doing here in this equation? I'm taking this signal here, yes? I break this one into what? Into delta Q and delta I. Square delta I becomes what? Delta I square, delta Q square, yes? And what am I doing here? I am averaging over what? Over all points. How many points in the constellation? N points. Did you understand that or not? What am I assuming here, by the way? I am assuming that all the points are equally probable. Why? Why am I dividing by 1 over n? Because I'm assuming that the probability of each point is what? Is 1 over n. Yes? But these need not be the same. Depend on I. I equal to 1, I equal to n, and so on and so forth. Why am I taking the square root? Quickly. Why am I taking the square root? I'm taking the square root because this is a what? a voltage. And here, what am I measuring is a what? Is a power. Are you following that? So I'm taking the square root. Now, when you calculate this, and you will do it in your simulation, in the simulation that I will assign tonight or tomorrow, what are you going to do? You are going to divide it by the worst, by X max. Did you understand what I just said or not? Let me ask you a question. Do you see this one here? Does it have to be the same as this one here? Remember, only if you are using phase shift keying, all the amplitudes are going to be what? The same. But if you are using QAM means what? Quadrature amplitude modulation. The amplitudes are not the same. You agree? When you calculate the EBM, you divide it by what? The maximum, which means the one that is furthest away from where? From the origin.
Professor, we are about out of time, yeah.
Okay. We'll continue this next time. Okay, I wish you all a very nice spring break. I will try to ruin it tomorrow by sending you the first project, which is the systems oriented. Clear? Okay.
And this concludes EE 544 on Thursday, March 13th, 2014.
The time is 10 o'clock.